But it was the thinking outside the box, the ability to see a pattern where it does not appear one exists. Do you see the pattern now? Each of those is a perfect square with the digits reversed. Was that a mean-spirited question?
Yes.
Absolutely. Was it a question that would draw somebody's ability to think outside the box out? Yes. And when I asked them, I said, so did anyone ever answer that? And they said, yeah. Every person who ever answered the question got offered the job immediately. They said, that's the person we wanted working for us. Because their ability to see things that were not absolutely obvious. Now, we are never going to do anything that's complicated in this class. Will you in future classes? Yeah. But you will have done a whole bunch of stuff between now and then. Okay. Now, why are we doing all this? So that now we can look at very specific sequences and determine what they're doing. So, let's do something really simple like this. This sequence is going to be, let's say, 2n minus 3 over n plus 1. This is my sequence. And let's write out the first few terms. Just the first few. So the first term, n is 1. What am I going to get? Negative 1/2. Second term, n is 2.
Over 1/3.
N is 3.
3 over 4.
Okay, n is 4.
5 over 1.
Do you see a really clear, obvious pattern here? Probably not. Here's my question. All sequences are infinite. Does this sequence converge, diverge to infinity, diverge without limit? Hey, those terms sound vaguely familiar, don't they? This is why you always answer the limit questions that way, because you can't tell me the answer without taking a limit. So the next thing we're going to do, and this is the thing we're always going to do with sequences. This is what you always do with a sequence. You say, is it approaching a finite value? Is it going off to infinity? Or is it just all over the place, doesn't approach anything? Now, I purposely wrote the first few terms out. There's no pattern. There's no pattern. They're finite, but you can't tell where this is going. But if I take that limit, if all else fails, can I go like this? Is this true, this statement right here?
Yes.
And it is true for all values of n that I could possibly use, because I can only use values of n that are greater than or equal to 1. There's no problems there. N's not 0. Oh, what is that limit?
Limit is 2.
2. So just for fun, tell me what is A100? Might be more obvious now. Let me go out just a little ways. I mean, 100 isn't much compared to infinity. But let's go out 100 terms. Now I'd have 197 over 101. Oh, that's a lot closer to 2, isn't it? If I went 1,000, now I'm 1,997 over 1,001. That's very close to 2. Okay, so how do we answer this question? The question is, does this converge? Does this diverge? And if it converges, what does it converge to? So our answer would be this converges to 2. Is there any value of n that it will ever equal to? Will an ever equal the number 2? No, it's approaching 2. The limit and the values are never going to be the same thing. But clearly, it converges to 2. So that's the question we want to be able to answer. So the quiz that you guys turned in last day, they were limit questions, but technically, those are exactly the things that we're going to see when we do sequences. We're going to be taking limits of the exact same kinds of things. Okay? So that one wasn't too bad at all. How about
Oh gosh.
We will see stuff like this.
Yeah.
Yeah, we don't love stuff like this, but we will see stuff like this.
Yeah, we can do.
Now, I'm gonna have to take a limit, but clearly, n cubed grows without bound, but 3 over n cubed is approaching 0, and so the sign of that's approaching 0. So what is the form this one's approaching?
Infinity times zero.
Infinity times 0. Can I work with that yet?
No, you have
No, that's the one we need to make into a quotient. So you're gonna throw it downstairs as a cosecant, right?
and
Cosecant downstairs?
Oh, we can put n cubed downstairs.
Yeah,
and make it approach 0.
remember, cosecants and cotangents are evil. Please remember that. Because if you don't, you're gonna make this really, really hard. No, I'm not doing anything, I'm just rewriting the problem. But now, as n grows without bound, both numerator and denominator are gonna approach 0, aren't they? Why is that a good thing?
Because now we can use L'Hopital.
Now I can use L'Hopital's rule. Exactly. It is possible to do an algebraic solution of this using rules of signs and things, but it's too complicated. I'd rather just use L'Hopital's rule. In this context, it's one step and out. So when we do the limit now, as n goes to infinity of this, all right. Well, on the bottom, if it helps, think of that as n to the negative 3. So it's negative 3n to the negative 4. Oops. And on the top, it's going to be cosine of stuff. And what's my chain rule factor? Want to be 3 times this? Because they both have a 1 over n cubed, right? So what's my chain rule factor on top? So 3n to the negative 3, so negative 9.
Yeah.
Now both numerator and denominator are still approaching 0 for the moment, so why don't I cancel? Does anything else cancel?
The 3 and the 9?
Yeah. And how about the negatives?
Yeah.
So can I write it like this? Is that correct? Stare at that for a moment. Is that algebraically, are those the same? Yes? No? Maybe? Somebody take a chance. Look, if you're wrong,
Yes.
the worst thing is I'm gonna throw the pen at you, and I can't even reach anymore. So, as n grows without bound, my argument's approaching 0, so this is approaching 3 times the cosine of 0, which is simply
1.
3.
Well, total is 3. Cosine of 0.
3. Beautiful. That wasn't that bad.
Yeah.
This is why we learn L'Hopital's rule. We learn L'Hopital's rule not because we're just going to take limits for fun. No, because we're going to be taking limits of sequences. And a lot of times we get something strange and goofy. All right. Oh, so therefore, by the way, what's the answer to this question? This sequence
Converges
converges
to 3.
to 3. The last problems we were just doing, the improper integrals, you would say the integral converges to whatever, or the integral diverges. Here we'd say the sequence converges to 3. So it's the same kind of answer. So I would like to know, does this sequence converge or diverge? Well, okay, we can start putting values in. Let's do this. Let's do the first few terms, okay? And go ahead and give me, by the way, you have to be in radian mode, don't you?
Hold on.
So let's just keep it simple. Let's do 2 decimal place approximations, just to be efficient. Make sure you're in radian mode.
Turn to radian.
Okay, so I want cosine of 1,
1.
and that's approximately,
The 0.54.
all right, now let's do cosine of 2, and that's approximately
Negative.
negative 0.4 to 2 decimals. Now let's do cosine of 3, and that's approximately negative 0.99 to 2 decimals, because 3 is close to pi. And then we do
And now we're
cosine
going
of
up.
4. Aha, and that's clearly we're getting somewhere. And now we do cosine of 5. And now we're back to positive now. So clearly these numbers are,
It oscillates.
they're all over the map.
Yeah.
In fact, I'm gonna have a few positives in a row, then a few negatives in a row, then a few positives in a row. Why are they all over the map? You just said it.
Taking the limit of a true function.
Right, the cosine is going to bounce between -1 and 1 forever and ever and ever and never approach any specific value.
Right.
Oy!
So
First of all, tell me about the limit.
the limit is
Just in the
from,
words limit, remember, limits are finite, infinite, or does not exist. So first of all, tell me about the limit.
limit does
The limit does not exist. The question is, does the sequence converge or diverge? What's your answer?
converges
Diverges,
Oh.
how?
without bound.
Without, no, not without bound. Without bound would mean infinite. Without limit. No, without bound, unbounded means it's infinite.
Okay.
That's what the term unbounded means.
Right.
There's no upper limit. Or it could be lower limit too. Because the limit was a D&E, we say the sequence diverges without limit, because there wasn't one. What if the value of my limit was infinite? Then we say the sequence diverges to infinity, right? It's just growing without bound. That's where growing without bound would be infinite. But this one, you just said, oscillates forever. So can I take a simple function and still get a D&E? Yeah. We don't work a lot with sequences in general. We don't work a lot with transcendental functions. We mostly work with algebraic functions, okay? Partly because they're just not very friendly. All right, let me change the problem. Totally different problem. Oh, I just made it way better, didn't I? Now, as I start plugging in numbers, I'm still going to be all over the map.
Because we have
Yeah. Now, I'm going to remind you of something that you saw in Calc 1, and it helped prove a couple of really important theorems, really simple theorems. It was called the squeeze or sandwich theorem. I'm going to remind you, because this one's actually a really important theorem. It's so easy to express them. The squeeze or sandwich theorem is how we proved the limit of sine x over x as x goes to 0. We put it between two other limits, and then we were able to evaluate it. We actually do that one all the way out in Calc 1. So let me show you. This one, if I drew a picture, all right, I've got three functions. Okay, we're just between a and b. So I've got here, okay, this will be y equals f of x. Okay, this will be y equals g of x. And then the third one, the fun one, that'll be y equal h of x. You notice I'm purposely having it touch.
Right.
Okay, so the squeeze theorem, in simple terms, as long as I'm continuous over this interval, I don't care what's happening that way, I don't care what's happening that way. In this interval, all three functions are continuous. And I'm saying in this interval, g of x is always less than or equal to h of x, and that's always less than or equal to f of x. Do you all agree with that statement?
Right.
So the squeeze theorem says if you pick any value between a and b, let's just call it c, any value between a and b, then the limit as x approaches c of g of x is less than or equal to the limit as x approaches c of h of x. Because it's continuous, all the limits will exist. That's why that part's important.
One is x versus c.
Of f of x. So if the functions maintain this three-way inequality, then the limits will. That's kind of an oh-duh, isn't it? We love this theorem because it makes so much sense. But it's actually how we've derived some very, very powerful conclusions in Calc 1. Well, let's check something out. True or false? That's not good. I don't know. Technically, they would be strict inequalities only because we're never going to be multiples of pi, but we'll say in general. All right. True or false?
True.
Oops, not X. I'll ask the question in a moment. This is not a trick question. This is not supposed to yield complication. True or false?
True.
By the squeeze or sandwich theorem. Some books call it the sandwich theorem, some call it the squeeze theorem. I say both because you've heard one of them, but maybe not the other, and I don't want you to ever be confused. We all agree with this three-way inequality, therefore this would be true also. I have no idea what this approach is, but I do know this limit is what?
0.
And that's got to be less than or equal to this,
Which is less than
which is less than or equal to?
0.
So it's
That'd be equal
zero.
to-
I don't know what it is, but it's somewhere between 0 and
Zero.
0. So, can you give me a conclusion?
Yeah.
The limit is 0, so this converges to 0.
Okay.
It's kind of clever, isn't it? I didn't come up with that. It's kind of clever because the cosine did not converge. So how come this converges? There's a term that you probably haven't heard in your physics course yet. You will. And you don't need to know for this course. You will deal with this next semester. We just said what the cosine graph looked like. It oscillated forever, but now I'm dividing it by something, so it's still going to oscillate forever, but the oscillations are getting smaller and smaller and smaller. That's what just happened. When I divide by a bazillion, aren't those values going to be tiny, tiny decimals? Sometimes they're positive, sometimes they're negative, but they're all getting close to 0. This is what is called harmonic motion.
Whoa.
Have you ever heard that term before?
Yes.
When you hear the term harmonic, what you should always think of as oscillations. Sines and cosines are harmonic functions. Harmonic motion means I'm oscillating. So if they're getting smaller, it's called damped harmonic motion because they're getting smaller. That's severely damped harmonic motion. And I say jokingly, bad shock absorbers, good shock absorbers. You ever been in a car where you hit a bump and you seem to oscillate for a while? Well, come ride with me today. You'll know what that experience is like. But people don't fall asleep in my car. Because you feel every bump for a little while. This is you hit a bump, you return right to normal. The functions that generate all of these are really similar in nature. This is severely damped. So we always study damped harmonic motion because in real life, I throw the rubber ball, it's going to bounce forever. No. At some point, it's not going to. Why won't it bounce forever?
Gravity.
Big G, good. Gravity. Yeah. What if we're in a vacuum? What if there's a vacuum and there's no gravity? There's nothing. There's no air resistance, and we're doing our training for the space flights and all that. Well, first of all, when I bounce it, it's just going to keep going. But yeah, so there's certain phenomena that we study later. It's kind of cool stuff. You don't need to know the function. You need to know the word. So if I have harmonic motion and it's getting smaller, then clearly when you're looking at this, you can go, oh, I see why the limit is 0. I can see it right in front of me. So if you were to graph that thing, it would look like this. That's why, and by the way, that's not an answer. You can't prove the answer by the picture. You did the problem, but the picture kind of confirms what you just said. Go, oh, that makes perfect sense to me. That's kind of the way I want you to think about it. Okay? All right, so this is where we are. Stop that, Chase.